Hello, I'm Dr. Maurice Dupre, and in this section we're going to discuss first-order linear differential equations. Linear differential equations are one of the most important classes of differential equations, and the first-order linear differential equations arise in many applications. Unfortunately, the method of separation of variables does not generally apply to these linear differential equations, and so we have to develop other techniques. Let's look at some definitions and see how we're going to go. Well, for the first order linear ordinary in parenthesis differential equation, that is a first order ODE, the standard form is dy over dx plus p of xy equals q of x. We call this the standard form. So the thing that you can notice about this is the reason it's called linear is that the derivative appears to only the power 1 and the variable itself only appears to the power 1, being multiplied by some function of x alone. On the right-hand side, I have a function of x alone. Sometimes this is called this operator, which takes a function y and produces derivative plus p times y, is called, in fact, a linear differential operator. In any case, let's consider that for a moment. Why won't separation of variables work? We've got an equation dy over dx plus p of x y equals q of x. How would I try and solve this if I wanted to use separation of variables? Well, I'd move this term to the other side. Dy over dx equals q of x minus p of x times y. And now what I'd have to do is say, well, we've got to write this as a function of x times a function of y. But the only way I can do that is to be able to factor out this p of x from this term and get something like 1 minus y. And in order to do that, the q of x would have to equal the p of x. And so since generally these two functions are different in these linear differential equations, separation of variables is not going to work. And so consequently, we have to learn a new technique, and that's something you'll have to keep in mind. Well, in the case of differential equations, sometimes we can find a function of the independent variable, which when we multiply both sides of the equation by that function, we get a new equation which is easy to solve. Generally, this type of technique is called finding an integrating factor. The function you multiply both sides by is called an integrating factor, and that's the technique we use to solve first-order linear differential equations. It's called the technique of finding an integrating factor. Let's see how we can do that. To solve the linear equation y prime plus p of xy equal q of x, multiply both sides by the integrating factor v of x, which is given as e to the antiderivative of p of x dx. That is, we look at the coefficient of y, we form its antiderivative, and then we form e to that antiderivative. That is, v of x is e to the antiderivative of p of x dx. So that's what you have to remember. Now notice, if v is e to the antiderivative of p, then v prime is p times v. That is, how do I differentiate this? Well, remember, to differentiate e to anything by the chain rule, it's still e to that thing, which is v, multiplied by the derivative of the function up there in the exponent, and the derivative of the antiderivative of p is p. So v prime equals pv. Notice what happens when I differentiate v times y. V times y prime will be vy prime plus the derivative of v times y, but the derivative of v is pv, or vp. So notice we get vy prime plus vpy. Factoring out the v, we get v times y prime plus py. So what this means is that when I've multiplied both sides of the equation by v of x, the left side has just become Vy prime. In other words, we get Vy prime on the left equals VQ. Now it's easy to find the answer because to complete this, you just integrate both sides. Notice the antiderivative of Vy prime is just Vy. And so you get Vy is the integral of VQ plus, of course, a constant of integration. Then we just divide through by V and we get the answer. So that's the technique of solving a linear first-order differential equation by using an integrating factor. Well, let's look at the solution of the first-order linear differential equation using the integrating factor in just a little bit more detail. Remember, the integrating factor is V equals e to the antiderivative p, and so the left side of the equation becomes Vy derivative equals VQ. And remember, here our equation is y prime plus py equals q, for short, where I've suppressed the independent variable x here. And so suppressing x's and dx's, then we can write for short Vy is the antiderivative of VQ plus a constant of integration. And so y is 1 over v times the antiderivative of VQ plus c over v. That is, we can actually solve for y just by dividing through by v. Notice v, being an exponential, is non-zero. So 1 over v is e to the negative of the antiderivative of p. So we can write the solution in general of the first-order linear differential equation y prime plus py equals q is y equals e to the negative antiderivative p times the antiderivative of e to the antiderivative of pq. In other words, all that product is to be anti-differentiated here, and plus an arbitrary constant of integration times e to the negative antiderivative p. Now let's solve a first-order linear differential equation by finding an integrating factor. So here we want to solve the equation xy prime plus 3y equals sine x over x squared. The first step is to put this in standard form. That is, we want y prime plus function of x times y equals function of x alone. So we divide through by x. We get y prime plus 3 over xy equals sine of x divided by x cubed. So now we see an effect that in our standard form, this 3 over x is what corresponds to the p. And so our integrating factor is v equals e to the antiderivative 3 over x dx. Well, the antiderivative of 1 over x is natural log x, so this is e to the 3 natural log x. Now, technically here I should put in an absolute value of x, and this would be equal to e to the ln absolute value of x, quantity cubed. E to the ln of any positive number is just that positive number, and so we get simply absolute value of x cubed. So let's restrict to the case where x is positive. And so let's add x greater than 0 here. And then our integrating factor is x cubed. And so we take this original expression right here then and multiply both sides by x cubed now. So we'll have x cubed y prime plus 3x squared y equals sine x. Notice that the left side is now the derivative of x cubed y, because look what happens when I differentiate x cubed y. X cubed y prime is x cubed y prime, that is, the quantity x cubed y differentiated is x cubed y prime, plus the derivative of x cubed, which is 3x squared times y by the product rule. And so here, then, the left side is just the derivative of x cubed y equals sine of x. Notice what's happened. I ignored the condition that x be positive. If I ignore it, the x cubed still works as an integrating factor, and so that's one thing to keep in mind. Sometimes when you're using the exponential and you end up getting exponential of a logarithm of an absolute value, if you try dropping the absolute value, but be careful, you'll see that what you get is an integrating factor that works. Okay, so here we've found the integrating factor as x cubed, and so consequently x cubed y is equal to the antiderivative of sine x plus a constant of integration. So the antiderivative of sine x is negative cosine x, and then we have plus our constant of integration. Well, let's clean this up a little bit. We had simply x cubed y equals negative cosine x plus constant of integration, which I'll write as constant minus cosine x, and now to solve for y, we just divide both sides by x cubed, and we get y equals c minus cosine x, all divided by x cubed, where c, of course, is our constant of integration. Let's look at a problem involving a first-order linear differential equation where we solve it using the integrating factor. Okay, we want to solve xy prime plus 2y equals 1 minus 1 over x for x greater than 0. Begin by putting the equation in standard form. That is, we want to have our leading coefficient term here just having coefficient 1. That is, we want the y prime by itself. So we divide through by x. We get y prime plus 2 over x times y equals 1 over x minus 1 over x squared. Now we see here the coefficient of y is what's being called p in our notation. P is 2 over x, and so our integrating factor v is e to the antiderivative p, which is e to the antiderivative 2 over x, which we'll write as e to the 2 ln x, which is x squared. That is, e to the ln x quantity squared, and e to the ln x is x. Now, why didn't I have to have an absolute value to worry about here? Well, x is greater than 0. So see, our integrating factor v is simply x squared. So now we multiply through by x squared, and we get the equation x squared y prime plus 2xy equals x minus 1. Notice the left side is simply the derivative of x squared y. So we have x squared y quantity prime equals x minus 1. And that tells us that x squared y itself, let's come up here, x squared y is simply the antiderivative of x minus 1, which is, of course, x squared over 2 minus x plus a constant of integration. And so now we can divide through by x squared everywhere to get the final solution. Y equals x squared over 2 divided by x squared is a half, minus x divided by x squared is 1 over x, plus c divided by x squared. And so there's our general solution to this first-order linear differential equation. Now let's solve a first-order linear differential equation where the first thing we have to do is put it in standard form. We want to solve the equation 2y prime equals e to the x over 2 plus y. Why don't you pause the video and try this one on your own and then see how I do it. Okay, well, I hope you remembered that the first thing you're going to have to do is put this in standard form. So we begin by moving the y term over to the left, 2y prime minus y equals e to the x over 2. So now divide through by 2 so that our coefficient of the y prime is simply a 1, and we get y prime minus 1 half y equals 1 half e to the x over 2. Well, notice in standard form that would be y prime plus negative a half y equals 1 half e to the x over 2. And so consequently, we see that where we've been using p for the coefficient of y, our p is negative a half. And so the integrating factor, remember, v is e to the antiderivative of p, and so we have to find the antiderivative of negative of a half, which is, of course, negative 1 half x. And so consequently, this is e to the negative x over 2 for our integrating factor. And so now what we need to do is multiply both sides of this equation through by e to the negative x over 2. So let's come back up here. We'll take this equation, multiply through by e to the negative x over 2 on the left, and by e to the negative x over 2 on the right. And notice on the right side, the e to the x over 2 simply cancel out, and we get simply a half. On the other hand, we know over here on the left, we're just going to get what in effect is the derivative of e to the negative x over 2y. So the derivative of e to the negative x over 2y is simply equal to 1 half. Well, that's a pretty easy equation to solve. If we anti-differentiate both sides, the right side antiderivative is simply 1 half x. So look what we're going to get. E to the negative x over 2y equals 1 half x plus a constant of integration. So consequently, to solve this, all I have to do is multiply both sides by e to the x over 2. We get y equals 1 half x times e to the x over 2 plus constant of integration times e to the x over 2. That's the general solution of our equation 2y prime minus y equals e to the x over 2. Now let's solve a first-order linear differential equation where we're having to deal with trig functions. Here I have the equation sine theta dr d theta plus cosine theta times r equals tan theta. In other words, theta is our independent variable and r is our dependent variable. So to put this in standard form, let's divide through by sine theta. So we get dr d theta plus cosine theta over sine theta, that's cotangent theta, times r equals tangent theta over sine theta. Well, remember, tangent theta is sine over cosine. So consequently, when I divide by sine theta, the signs cancel, and on the right side, we're just going to get 1 over cosine theta, which is secant of theta. So now we see, in effect, the thing we call P is cotangent of theta. So V is e to the antiderivative of cotangent theta. Well, the antiderivative of cotangent theta is natural log of absolute sine theta. So here we'll get e to the natural log absolute sine theta, and so that's absolute value of sine theta. So what we want to look for is that sine theta is an integrating factor. Let's multiply through the equation back by sine theta. Notice if we do, we just divided through, we'll get back to the original equation. So in effect, the original equation was an equation in standard form that had been multiplied through by its integrating factor. In fact, notice what happens if you differentiate sine theta times r with respect to theta. Let me put the d by d theta here because we're dealing not with x and y but with r and theta. If I differentiate sine theta r with respect to theta, I'll get sine theta dr d theta plus cosine theta r. And so here we have simply then the derivative of sine theta r is tangent theta, and so consequently sine theta r is equal to the antiderivative of tangent theta d theta. Well, the antiderivative of tangent theta is simply natural log of absolute value of secant theta plus a constant of integration. So let's write this down then. We have sine theta multiplied by r is the natural log of secant theta plus a constant. And so now we can divide both sides through by sine theta to solve for r. R is the natural log of secant theta, absolute value of secant theta, over sine theta plus c divided by sine theta. 1 over sine theta is cosecant theta. So we could write this as r equals cosecant theta multiplied by natural log absolute value of secant theta plus constant of integration times cosecant theta. Now let's solve an initial value problem for a first-order linear differential equation. Solve the initial value problem, dy dt plus 2y equals 3, with the condition y at 0 equals 1. This condition y at 0 equals 1 is what makes this an initial value problem. Notice the differential equation itself is already in standard form, and so this coefficient of y is what we've been calling p. And so that, remember, v is e to the antiderivative of p, which is e to the antiderivative of 2. Now our independent variable is t, so that's antiderivative of 2 integral 2 dt, and so that is e to the 2t. So our equation becomes e to the 2t dy dt plus 2e to the 2t y equals 3 e to the 2t. And notice, as usual, the left side is now the derivative of v times y. That is, if I differentiate e to the 2t y with respect to t, notice we're going to get e to the 2t times dy dt plus the derivative of e to the 2t times y, but the derivative of e to the 2t is 2e to the 2t, and so there we have the left side. And now the right side is simply 3e to the 2t. And so that tells us that we have only to anti-differentiate e to the 2t to arrive at the final solution. E to the 2ty differentiated with respect to t is 3e to the 2t. And so that means e to the 2ty is the antiderivative of 3 times the antiderivative of e to the 2t dt plus constant of integration. And so antiderivative of e to the 2t, of course, is e to the 2t over 2. So we get 3/2 e to the 2t plus our constant of integration. Now to solve the problem, we multiply through by e to the negative 2t on both sides, and we'll get y equals 3/2 plus c e to the negative 2t. That's our general solution to this differential equation. But remember, we want y at 0 equals 1. So we're going to replace everywhere t by 0 and set the resulting value of y equal to 1. So y at 0 equals 1. On the other hand, from its expression here in terms of this functional relationship, y at 0 is 3/2 plus c e to the negative 0. Well, that's e to the 0, which is 1. So 1 equals 3/2 plus c, and so therefore c itself is just negative 1/2. And so consequently, we come back here and put negative a half in for the c, and we find our particular solution as y equals 3/2 minus a half e to the negative 2t. One of the common applications to first-order differential equations is to problems involving mixtures where we have certain solutions going into a tank and stuff running out of the tank, and the question is, what's the actual concentration at time t? Well, let's look at an example. Fertilizer mixture. A tank contains 100 gallons of fresh water. A solution containing 1 pound per gallon of soluble lawn fertilizer runs into the tank at the rate of 1 gallon per minute, and the mixture is pumped out of the tank at the rate of 3 gallons per minute. Find the maximum amount of fertilizer in the tank and the time required to reach the maximum. Okay, so let's sketch a rough picture of our situation here. We've got a tank, fertilizers coming in and fertilizers draining out. Now, the tacit assumption here is that what drains out is a complete sampling of the homogeneous mixture in the tank. That is, we're assuming instantaneous mixing of what goes in with everything else in the tank. What's going in is given to us as 1 pound per gallon mixture, and it's coming in at the rate of 1 gallon per minute. 1 pound per gallon, 1 gallon per minute. What's going out is 3 gallons per minute, but of course, as far as how many pounds of fertilizer is in what goes out, that depends on the concentration at the time it goes out. One thing we can figure out is the amount of water in the tank at time t. After all, there's 1 gallon going in per minute and 3 gallons going out, so that's a net of 2 gallon loss per minute, and so that means after t minutes we'll have lost 2t gallons. Starting at 100 gallons then at time t, the volume is 100 minus 2t. Now what we need to write down is a symbol for the amount of fertilizer in the tank at time t. So I'll let y of t be the amount of fertilizer in the tank at time t. And so what we know is that dy dt, that's the rate of fertilizer going into the tank, or net rate, is the rate that it goes in minus the rate that it goes out. Well, we can easily figure out the rate that it goes in because 1 pound per gallon is the concentration, and 1 gallon per minute goes in. So 1 pound per gallon times 1 gallon per minute is 1 pound per minute. So what's going in amounts to 1 pound of fertilizer per minute. Now, for the rate of fertilizer going out, we need to calculate the concentration at time t. For the rate out of fertilizer, we need concentration at time t. The concentration at time t is y of t divided by v of t, and of course v of t is 100 minus 2t, so that's y of t divided by 100 minus 2t. So that's the concentration in pounds per gallon, and so if 3 gallons is going out per minute, that means 3 times y of t over 100 minus 2t is the rate out, whereas the rate in, remember, is simply 1. We already figured that out. So that means dy dt is the rate in 1 minus 3y of t over 100 minus 2t. In symbols, that means that dy dt equals 1, the rate in, minus 3 times y over 100 minus 2t. Remember, this we figured was the rate out. And so this is clearly a linear first-order differential equation. We begin by putting it in standard form, and that means moving the y term over to the same side as the dy dt. So we get dy dt plus 3 times the quantity y over 100 minus 2t equals 1. Well, remember, the coefficient of y is the symbol, is the thing we've been calling p, and so that's what we have to anti-differentiate to compute our integrating factor. So p of t is 3 divided by 100 minus 2t. So in our usual notation, we use v for the integrating factor. So v is e to the indefinite integral of 3 over 100 minus 2t dt, and of course that's e to the negative 3/2 ln 100 minus 2t. Notice I've left out the absolute value here. Why? Well, in this problem, this 100 minus 2t represents the amount of water in the tank at time t, and so that's always greater than 0 for the range we're interested in. So I can drop the absolute value, and that means v itself is simply 100 minus 2t, all raised to the negative 3/2 power. So when we multiply our equation both sides by that integrating factor, the left side is just the derivative with respect to t of the integrating factor times y, and the right side is what we get by multiplying the right side by this. But remember, our right side was simply 1, so the right side is just 100 minus 2t to the negative 3/2. And so consequently, 100 minus 2t to the negative 3/2 y is the antiderivative of this quantity, which is easily seen to be just 100 minus 2t to the negative 1/2 plus a constant of integration. In other words, if you differentiate 100 minus 2t to the negative 1/2, well, you're going to get a negative 3/2 power times a negative 1/2, but then you're going to get from the chain rule a negative 2 coming out as well, and so the negative 2 cancels with the negative 1/2, just leaving a 1. And so there we easily have the antiderivative. And so multiplying both sides by 100 minus 2t to the 3/2, notice what's going to happen. When I multiply something raised to the 3/2 times something, that same thing to the negative 1/2, I just get that thing to the first power. So we're going to be multiplying both sides by 100 minus 2t to the 3/2. So that changes the first term to 100 minus 2t plus c times 100 minus 2t to the 3/2. So that, in effect, is the general solution to the first order linear differential equation that this problem gave us. However, we know something else about our situation. When we start at time t equals 0, there is no fertilizer in the tank, and that means we know y at 0 equals 0. In effect, that's given us an initial value problem. Since y of t is 100 minus 2t plus c times 100 minus 2t to the 3/2, what we do is replace everywhere t by 0, and so this term just becomes 100, this becomes 100, and we get 0 equals 100 plus c times 100 to 3/2. Of course, the square root of 100 is 10, and 10 cubed is 1,000, so 0 equals 100 plus c times 1,000. And that leads to 1,000c equals negative 100, so c is negative 100 divided by 1,000, which is simply negative 1/10. And so we replace the c, this general constant of integration, in our general solution by negative 1/10, and there we have the amount of fertilizer in the tank at any time t. Y of t equals 100 minus 2t minus 1/10 times the quantity 100 minus 2t, all raised to the 3/2 power. Now, we didn't just want to know what came into the tank at time t for any time t. We wanted to know the maximum value that y could have and what value of t gave that maximum value. We could use our typical optimization procedure to do that. That would be differentiate this, set the derivative equal to 0, and solve for t, and then put that value of t back in to find y. But remember, we started with a differential equation in the first place, and so let's look back at our original differential equation and see that that actually simplifies the problem. Notice our differential equation is dy dt plus 3y over 100 minus 2t equals 1. At the maximum value of y, we have dy dt equals 0, and so our original differential equation tells us simply 3y over 100 minus 2t equals 1, or 3y is simply 100 minus 2t when the maximum happens. So that means when we look at our equation for y is 100 minus 2t minus 1/10 100 minus 2t to the 3/2. We can replace in each place here this quantity 100 minus 2t with the 3y, and that gives us a very simple equation for the maximum value of y. The y maximum satisfies y equals 3y minus 1/10 3y quantity to the 3/2 power. And so we can solve that very easily for y. Notice that what we can do is begin by rearranging. We cancel y's here. This puts a 2y on the right and move this to the other side, and we get 1/10 3y quantity to the 3/2 equals 2y. Well, multiplying through by 10, that gives us 3y to the 3/2 power is 20y, and 3y to the 3/2 means 3 to the 3/2 times y to the 3/2, so that's equal to 20y. And so now divide through by y to the 3/2, and we get simply 3 to the 3/2 is 20y to the negative 1/2. And so we can turn this into y to the 1/2 on the right, and we get square root y is simply 20 over 3 to the 3/2. And so now square both sides. When we square both sides, the square of 20 is 400, and the square of 3 to the 3/2 is 3 cubed. 3 cubed is 27, so the maximum amount of fertilizer that will ever be in the tank is 400 over 27 pounds. And notice we didn't have to go back to our solution to the problem, differentiate it, set the derivative equal to 0, solve for t, and then plug that value of t into the function. We found the maximum amount of fertilizer in the tank was 400 over 27 pounds. Without finding the time at which that occurred, we did that by using the differential equation itself instead of using the solution, differentiating it, setting its derivative equal to 0, and solving for t. And so you might think, well, since we're asked to find that time at which the maximum occurs, we're going to have to do that anyway. But no, let's see how our differential equation actually gets us around that as well. Remember, at the maximum, we have 3y equals 100 minus 2t. We've now worked out that y at the maximum is 400 over 27, so we simply substitute that value in for y in this equation, and notice we get a very simple equation for t. 3 times 400 over 27 equals 100 minus 2t, and so 100 minus 400/9 equals 2t. In other words, we cancel 3's here. So that means since 100 is 900/9, 900 minus 400 is 500. So we have 500/9 equals 2t, or t is 500 over 18, which is 250 divided by 9 in minutes for the time there. So, well, in actuality, that's about 27.78 minutes. But there it is exactly, 250 divided by 9 minutes is the time at which the maximum occurs. So just to emphasize our final result, the y maximum is 400 over 27 pounds, and that occurs at t equals 250 divided by 9 minutes. Well, we've solved some first-order linear differential equations using the method of the integrating factor, and we've solved some initial value problems. Also, we've solved the mixture problem, and remember, when you're dealing with mixture problems, you want to figure the amount of the stuff in solution, not just the concentration. By figuring the amount and the volume, total volume of solution in the tank at time t, that's how you're able to figure out the rate in minus the rate out.